Okay, thanks very much. Thanks especially to the organizers for the invitation. I'm going to talk about something a little bit different. Talk about searches for more specifically short-range spin-dependent interactions with fairly heavy concentration on what are considered axion searches, or searches that could possibly have more likely to have implications for the strong CP problem. So the motivation I've already mentioned is that, well, at least recently it appears that these kinds of experiments will be able to address the strong CP problem directly, doing experiments in the so-called axion window. But more generally, these so-called weakly interacting sub-EV particles, or WISPs, as referred to in Andreas's review a few years ago, are generally expected in theories beyond the standard model. These kinds of experiments can go on those. And even more generally, and especially as an experimentalist, I'm interested in this third motivation here. Why look for these things? Well, why not? The parameter space for these interactions is wide open in some cases. The technologies in the search engine regime is good enough reason to do so. Okay, but more on the specific motivation of addressing the strong CP problem. Okay, I'm going to assume that the most promising solution to the strong CP problem is in fact the axion. Okay? And by axion, I mean the usual QCD H-equal axion, which arises from the breaking of an additional V1 symmetry at some scale of FDQ. The fifth force, or the short-range spin-dependent force interactions, are different in two major ways from most of the experiments we've heard about so far. I'm going to copy this classification of by no means exhaustive list of axion and axion-like particles experiments from Geraci. Plotted the axion, not just the coupling, which could be to photons or to matter, but to arrange them in terms of the axion source. Okay, for cosmic axions, essentially dark matter experiments, for couplings to photons, this is EFX and resonant cavity type experiments. We're going to hear about the Casper experiments, which is still a cosmic search, but the coupling in this case is to matter. There are solar axions, which you can pull in the experiments like CAST and AXO. These experiments, one advantage of the short-range force experiments is that the sources, like the light shining through walls experiments, the sources, the axion is sourced locally, so that they're sensitive to axions or axion-like particles, even if they do not constitute a major component of dark matter, and they're distinguished by the coupling they forward is the coupling to matter. And I'll be talking primarily about torsion balance experiments and magnetometers, and briefly mention the Ariadne experiment in some detail, which has promise of much bigger sensitivity than the traditional regime of these experiments. Okay, and what do I mean by short-range experiments? Well, roughly speaking, it's coincidence with what I would call the traditional axion window. So here's the relationship between the axion mass and FPQ, or the way I like to think about it is in terms of the range of the Compton wavelength of the axion and FPQ. The experiments that we do are very low energy, non-relativistic, macroscopic experiments, so I can think of things in terms of SI units, interaction ranges, macroscopic interaction ranges. And by the traditional axion window, I mean the range between about 10 micro eV and between 10 micro eV and 10 milli eV, okay, where the upper bound is determined by astrophysical and laboratory bounds, the blue and gray bars here, and below, assuming a post-inflationary H-equal symmetry breaking scenario, by the dark matter movement on the low mass side, or the high interaction or the long interaction side. So the axion window, or the range of these experiments, is between about runs from about 20 microns to 2 centimeters. Okay, what kinds of spin-dependent forces can we look for? Okay, these were the ones I'm going to talk about are primarily from this classic reference by Moody and Wilczek many years ago, which they consider, for instance, the so-called spin-spin or dipole-dipole type of interaction, which is mediated between two fermions with masses Ma and Mb. There's a pseudoscalar coupling, pseudoscalar couplings at both of these vertices here. This is the potential for this interaction is described by this long formula here, where sigma A and sigma B are the spins of the two particles. R is their separation. This combination GA and GB is the coupling constant. It's the strength of the interaction on some absolute scale, well, relative scale, but it's relative to the strong interaction, which is an ordered unity. Particles A and B here could be any fermion in the first generation. Lambda here is the interaction range, or if you like, the Compton wavelength of the mediating particle, which could be the axion. It's a kind of a messy formula, but in the limit of a massless particle exchange, it just reduces to the usual magnetic dipole-dipole interaction. So it's a generalization of the magnetic dipole interaction for the case of a massive mediator. And I should mention, yeah.
Can you have monopole dipole?
Yeah, I'll get to that in a minute. I wanted to introduce this first of all because it's well, ostensibly or presumably one of the more familiar type of interactions. And I also wanted to emphasize that in the absence of a signal, and no experiment has seen a convincing signal to date, experiments will report their limits on this coupling constant over the range of the interaction of the range of masses, or the interaction range of which they're particularly sensitive. There are a number of examples of those exclusion laws. But yes, more interestingly, Moody and Wilczek also investigated this so-called spin mass or so-called monopole dipole interaction, which goes as the spin of the particle carrying the pseudoscalar coupling dot R. This combination, of course, violates parity, or it also violates time reversal symmetry, which is something we could possibly exploit in the future, but none of the experiments that I'm going to talk about now actually do exploit that. And I do want to mention that even though I was going to focus on spin-dependent forces, they also consider spin-independent forces in their analysis, which is, in other words, the traditional Yukawa type interaction, or the more traditional parameterization, which is given by this expression here in terms of some strength, relative to gravity. And until very recently, these experiments appeared to be potentially just as competitive for addressing the strongest heat problem as the spin-dependent forces. And they also play a role in the astrophysical limits that one gets from these astrophysical limits that one can set. Okay, Moody and Wilczek also derive expressions for the axion couplings, the pseudoscalar and the scalar couplings. Okay, these are simpler expressions than a lot of the expressions that have been presented this week, but they're on the same order as a lot of the so-called benchmark expressions that we've seen earlier this week. And I'm choosing to show them here for their simplicity, and they're pretty much in the same order as the so-called benchmark couplings that we've seen, which the sensitivity of which these experiments have been judged for a long time. So the pseudoscalar coupling in this model is just given by the mass of the particle carrying the mass of the polarized particle divided by FPQ. The scalar coupling, at least for nucleons, is given by this matrix element here, which evaluates to about 60 MeV. Here it picks up a factor of theta QCD divided by FPQ in this combination with quark masses. And we also have the expression for the axion mass, once again in terms of the FPQ. Okay, so I can use the expression for mass to eliminate FPQ and the expressions for the coupling, and this leads to the so-called axion predictions. Right, for the dipole-dipole interaction, the scaling is the dipole-dipole, monopole-dipole, and monopole-monopole expressions of the coupling is all predicted to go as 1 over the range squared. In the case of the dipole-dipole interaction, you just get a line bounded by the axion window in this parameter space. For the other two couplings, with the factors of theta QCD here, you have regions bounded above, at least by the limits on theta QCD. Okay, so finally getting on to some of the limits here. Here are the experimental limits, which I'm calling axion constraints for the nucleon-electron monopole-dipole case. That's this expression here. The experimentally excluded region, or the direct experiment, is above and to the right of these solid blue curves here. They come from spin-polarized torsion pendulum experiments, which I'll describe in a few minutes. The range runs from a centimeter down to about a micron. The coupling runs from, in this case, in this plot, 10 to the minus 35 up to 10 to the 20th. So at in the axion, the region of the axion window here, the coupling is about 10 to the minus 25. Okay, and roughly 9 orders of magnitude, okay, above what the axion prediction is. So here's the axion prediction. Okay, which comes, okay, from it's really an indirect limit which comes from the neutron-electric dipole moment. And this is the relationship derived in this paper by Cruther and Witten, okay, between theta QCD and the electric dipole moment of the neutron, which at the current limit sets the upper limit of theta QCD to about 10 to the minus 10. Okay, there are also astrophysical limits, where it's a combination of astrophysical limits that you get from the limit on the electron pseudoscalar coupling from white dwarf cooling arguments, okay, together with the scalar coupling constant that you get from short-range gravity unpolarized torsion pendulum experiments. Okay, so these are only about 2 or 3 orders of magnitude above the Okay, so the challenges associated with pushing the sensitivity of these experiments higher and higher. I can't describe all the systematics of a particular experiment in any detail, but in general, all of these experiments, okay, are fighting against very, very high, against rapidly increasing backgrounds, and to some extent the scaling problems associated with very small signals, because you have very, very small test masses. Okay, all of these experiments, the challenge is how do you get, you need spin polarized test masses, how do you get significant spin polarization without also introducing a huge magnetic background? Okay, that's extremely difficult, and the background, or these dipole-dipole type interactions will blow up according to very strong power laws, so that becomes a problem with short range. Even experiments in which you're doing monopole-dipole type experiments, where one or both, or at least one of the test masses is nominally non-magnetic in the presence of an external field or the field from the other test mass, you can still couple magnetically via the susceptibility of the two test masses, or via the conductivity. In the case when you have moving test masses, you generate eddy currents which are coupled together. You can shield against these forces here, but then again, if the more shielding you use, the more you're going to limit the proximity of the test masses, which becomes a problem, for example, for short-range investigations. Okay, and that problem is also exacerbated by the fact that you're running into this scaling problem here. These forces all behave with this, according to this bucolic type interaction here. So you can get as many spins, as big a spin source as you want, but it's not necessarily going to be all very useful. In order to investigate interaction with the characteristic range of lambda, essentially all of your spin and mass has to be concentrated in that range, or it won't have any effect. To a lesser extent, these experiments fight electrostatic backgrounds, even with conducting in well grounded test masses. You can still have forces due to electrostatic surface potentials, which blow up as 1 over r squared. And the shortest range experiments are also fighting against Casimir backgrounds, which are of interest in their own right. But these cannot be shielded below about a tenth of a micron, because the electromagnetic modes responsible for the Casimir force have to penetrate any shielding below the plasma wavelength, which is for most good conductors is about a tenth of a micron. So the particular experiments that I'm going to discuss are they're all trying to fight one or more of those particular backbones in clever ways. So here are the experiments that set the limits on one of those on the previous plot I showed. These are the spin polarized torsion pendulums in the net wash group. This is the ALP torsion pendulum, which we published several years ago. Consists of a nominally non-magnetic, very pure silicon pendulum element here. Note the use of flat, thin test mass geometry to overcome the scaling problems. You want to concentrate, it's a very efficient geometry for concentrating as much test mass at the particular scale of interest that you want to investigate. The spin polarized, the source of the spins were in this case the more polarized electrons, which were provided by this split toroidal electromagnet here. There's no shielding in this case. Okay, they're just relying on the very low degree of magnetism in their pure silicon test mass. I believe that the limits I showed you were still limited by a magnetic interaction, even though it's nominally non-magnetic. There was an interaction between the classical magnetic field of this magnet and the small but non-zero finite susceptibility of the silicon torsion pendulum. Okay, this is the more recent experiment from the university, from the Wash group. This gives you an idea of the size. This is the so-called 20-pole spin pendulum from a few years ago. So notice once again the use of a flat test mass geometry. They have a flat disk with their detection element suspended above a similar disk. Well, the lower force generating disk could either be the equivalent, or it could be or just another element of the same design, but made of pure copper. The force-sensitive pendulum part consists of these alternating tiles of different kinds of magnets. The green, illustrated in green here, are Alnico magnets, which consist in which the magnetism is solely due to the spins of the material. The blue magnets here consist of samarium cobalt, which has a significant orbital contribution to the overall magnetism. And they were very carefully designed so that the total classical magnetic moment of each of these tiles was as identical as they could make them. So even though you have these magnetic materials placed very close together, you can have a fairly substantial classical magnetic interaction, but it is not modulated. Okay, as the source disk turns under the pendulum. Okay, the total spin density, which is represented by represented by the arrows, is modulated at 1/20th of the revolution period. But the total classical magnetic moment, ideally, is not modulated at all. So it's an effective way of canceling subtracting out the background magnetization. Okay, that experiment, the 20-pole the 20-pole pendulum, was also used to set the most stringent limit to date on the electron-electron dipole-dipole interaction. Okay, this is the same experiment, but replacing the spin polarized as source mass with just one made of solid copper. I'm sorry, replacing the copper element with an identical spin polarized source as well. And they were able to set the limits described by this curve here, about 10 to the minus 15, at the range of the axion window. The astrophysical limits here is just once again, this is just the square of pseudoscalar coupling of the electron, which you get from the white dwarf cooling arguments. And that's many orders of magnitude below what the direct limit is. And here's the single line limit representing the axion prediction. Okay, moving on to nucleon monopole dipole experiments. Okay, that's this potential here where we've got nucleon couplings as well. Okay, what you do for the best limit, the best direct limit that on this particular interaction comes from well, you start with the it's deja vu all over again. You start with the xenon 129 helium-3 electric dipole moment experiment. You take out the high voltage, the high voltage source, and in place of it, you put in place of turning on and off a high voltage source, you modulate a dense, nominally non-magnetic source mass in close proximity to the magnetometer cell, and you look for a difference, or you monitor the relative precessions of the helium-3 and the xenon 129. Okay, as you move this nominally non-magnetic source mass piece of bismuth germanium crystal back and forth nearby, and in the absence of any relative precession frequency shift, they were able to set these limits 10 to the minus 27, 10 to the minus 28, the upper region, in the centimeter range here. Here, the astrophysical bounds are just below what they were able to obtain, where the pseudoscalar coupling to nucleons is fixed at about 10 to the minus 10 from the supernova 1987A neutrino signal. Here, the axion constraints for the neutron EDM experiment are limited above, okay, by the neutron electric dipole moment, and below, okay, there's actually a lower limit, which comes from the standard model prediction for the neutron EDM of 10 to the minus 32 e centimeters, which implies a lower limit of theta QCD to about 10 to the minus 16. Okay, I wanted to briefly mention what the spin-independent interaction, the limits of the experimental limits on the spin-independent interactions are, because they enter into these astrophysical constraints. Okay, the same curves that you see here, okay, are also these. Okay, I'm using a slightly different parameterization here. Here, alpha is the strength relative to gravity, which runs from 10 to the minus 7 up to about 10 to the 10th here. You can convert that between the two using this expression here. And here is the expression. Here is the axion prediction. Okay, for the monopole squared or the monopole interaction. And you can see that it's only about a factor of about 4 orders of magnitude below what the experimental limits are. Okay, the experimental limits here derive from torsion pendulum experiments, more head-wash experiments, on the high range end, and from MEMS and MEMS type experiments at the lower end. But they're only about 4 orders of magnitude above what the axion prediction gives you. And compare that to what the scalar pseudoscalar limits or direct limits were, roughly about 7 orders of magnitude above the axion prediction. The scalar pseudoscalar nucleon electron experiment gives about 9 orders of magnitude higher, and the pseudoscalar or the GP limit was 13 orders of magnitude higher than the existing than the axion predictions were. So that's even this shows that until very recently, there was just as much promise. There was just as much promise in getting access to the part of the parameter space of interest of the axion with unpolarized test mass experiments as well as polarized test mass experiments. In particular, here again are the unpolarized limits. There was a proposal from Ram Kalsic for I think a completely cryogenic torsion pendulum experiment with a new type of very, very low noise autocollimator readout system that he had designed, which looked as if it would get into within about an order of magnitude of the accion window in the unpolarized in this monopole parameter space. I don't know what the status of that experiment is. But going back to the parameter space for the nucleon monopole dipole interaction, the new experiment on the new experiment, which is just starting to come online, which I'm collaborating on at Indiana. It's the brainchild of Andy Geraci at Northwestern University. It's a collaboration between Indiana and Northwestern and the CAP facility in Korea at Stanford. It stands for Axion Resonant Interaction Detection Experiment. And it's somewhat like the static NMR experiment at Berlin, but the key insight is the key improvement in sensitivity comes from the realization. Comes from the realization, or comes from the realization that one can get a significant enhancement if one does a resonant experiment, and that is, instead of modulating doing a static NMR experiment where you're looking for the modulation of the Larmor precession frequency of the species, what you do is you modulate the nominally non-magnetic test mass at the Larmor precession frequency, and instead of looking for a frequency shift, you actually look for an induced transverse magnetization signal directly. And if you have a species that has an exceptionally high T2 relaxation time, for example, I think we're assuming about a 1 second T2 relaxation time for this polarized helium-3 cell, you can get an enhancement factor of several orders of magnitude relative to the static NMR experiments. Okay. So the projected limit for the Ariadne experiments, assuming I believe a 1 second T2 time is represented by this upper dashed curve here. 1,000 second T2 time, which has been attained in relatively high pressure polarized helium-3 cells, is what's represented by the lower dashed curve. Okay, so this promises to be the first experiment with sensitivity to the range of the axial parameter space that's implied by the neutron electric dipole. Okay, but of course the interactions that I described aren't the only possible interactions. Dobrescu and Maciu did a very general analysis a few years ago, a general study a few years ago, in which they considered and they asked what were the possible what were the possible interactions between polarized fermions, demanding only rotationally invariant, demanding only rotational invariance. And the non-relativistic single boson exchange limit, where they don't only consider spin zero scalars, but they allow for spin one exchange as well. They identified 15 possible different spin dependent interactions. So in addition to the standard dipole-dipole experiment, there are two additional so-called static spin-spin interactions. There are 6 additional interactions which involve the spin of both fermions as well as the relative momentum of the two. In addition to the classical monopole dipole experiment due to Moody-Kowalczyk, there are 4 other spin mass or other monopole dipole experiments, monopole dipole potentials, which also depend on the relative momentum. Okay, the couplings that I showed, those small g couplings in general are not they're not in general the most, or they're not the most general couplings. The f parameters here, okay, are a bit more general. They would usually be expressed as linear combinations of those g parameters. But by Dobrescu's count, there are 72 independent couplings, which are indexed by the type of the potential as well as the flavor of the fermion that's involved here. So the parameter space for these interactions is just worldwide. And just very briefly, I'll talk about some of the experiments that are being done, especially using nuclear techniques. Here's an experiment that was published a few years ago by our host. This sneaks up on this axial coupling, or spin-1 interaction in this potential, which goes as sigma dot b cross r. This experiment was done in a beam which used the method of Ramsey's method of separated oscillatory fields to compare the precession frequency, or to look for a precession shift of a beam of neutrons induced by this interaction as it passed very, very close to an unpolarized non-magnetic source mass, compared to the precession frequency of a reference beam spaced close by. And in the absence of a signal, they were able to set the competitive. They were able to set these limits that you see here in this parameter space for this axial ripple constant. And the fact that you can see how quickly the limits of the previous experiment cut off at a centimeter. So this is a micromolus experiment. One of these very sensitive comagnetometers at Princeton. Extremely sensitive, okay, but limited in the range, okay, because of the multiple layers of magnetic shielding that you have to use. Out of time? Oh, okay, thanks. Okay, this experiment inspired my colleague Mike Snow at Indiana to do a follow-up experiment, which in a nutshell is essentially the same experiment repeated with 10 times over simultaneously. He's got it's another polarized neutron beam experiment in which the target consists not of one slab, but of at least 16 slabs oriented in different directions, and with density variations throughout the target. This experiment has been run at the whole neutron beam at Los Alamos over the course of the last, from 2 years ago up until last year. They're just finishing up their data analysis, and his student Chris Haddock is finishing up the analysis, and the preliminary limit that they were able to derive, this may have been published in the last few weeks, is not surprisingly, given the extra number of test masses here, roughly an order of magnitude more sensitive than the previous limit over in the range of sensitive. Okay, so in conclusion, the spin-dependent experiments covered, was wanted to say, significantly more than the 10 square decades of the parameter space below 10 centimeters in the past several years. Many new channels have been identified, and especially experiments with NMR and other nuclear techniques will promise to have unique sensitivity, or many orders of magnitude more sensitivity than the last round of experiments. And there's also a chance to close the traditional axiom. Thanks.
clear talk. Questions, comments? Yes, please.
Just want to add that the electron-nucleon monopole dipole limit has been improved by one order of magnitude by our group in Italy, and the result is from Physics LPSC from 2017.
Thanks.
Okay.
Yeah, I'm sorry.
No, okay.
Can't do, yeah.
I mean, this is improving the Earth-Wash result.
Yeah, couldn't do justice to everyone.
In your plots on the monopole dipole bounds, so you had two lines for theta. I think it was 10 to the minus 10, and the other one was
10 to the minus 16.
10 to the minus 16. Yeah.
So is this maybe the sites that you expect in the standard model to be induced by the CKM? That's the reason?
Yeah. This is right. This corresponds to the upper limit on the electric dipole moment, 10 to the minus 26. And this is the standard model prediction. It's really the lower limit, if you will. There's a lower limit on this, on this interaction.
Okay. Thanks.
Of course, if you would be fast with your project, we will put down the limit for the detected EDM also. It means you have to hurry up to measure first EDM for this video, yeah?
Well, if we finish that, if we finish this first and we find a signal, you still have to do a. It's complementary to the EDM experiment. You have to find out. You still have to do the neutron EDM experiment. That take as much time as you want. Okay, in order to find out whether we found, whether we discovered the QCD axion or some other kind of axion.
Okay. So no more questions?
I'm working on both, so I have that covered.
This is very clever, of course. No more questions, comments? Okay. Thanks, both speakers again.